Alright guys, let's continue our next video on the matrix multiplication. In this video, I would like to cover the effect of transformation as a rotation. What happens when you multiply two matrices and the net effect of the transformation is a rotation of the matrix. And as a quick recap, in the last video, we were talking about the scaling down or scaling up version of the transformation. What happens when you multiply a scalar matrix and how does it scale up or scale down the input, right? So that's what we kind of discussed. So on the same lines, we'll be talking about the rotation. Instead of scaling, we'll be talking about the rotation. How does what kind of matrices or what kind of combination of matrices we can use to multiply and create the net effect of a rotation of an object or a rotation of the input. That's kind of the transformation we're talking about here. And if you see the screen here, I've taken a kind of image from the internet, right? So if you see here, this is our original square box, okay? So where we see the blue line in the positive x-axis and the red line in the positive y-axis, and this is our square over here. So what are the different types of transformations we can do on this square, okay? So there are kind of three kind of transformations they have given. Ignore the D1 because D1 is essentially scaling it up, like stretching it by multiplying by a scalar, which we already done. So this part is already done in the previous video. Let's focus on B and C. Primarily, we'll focus on B. And what is B? If you see, is rotation by flipping the columns. What does it mean is, in this case, if you take this as the input and if you want to flip this square 90 degrees anti-clockwise or counterclockwise in this direction, right? In this direction, where the red kind of comes here and the blue kind of moves up like this over here. If you see the blue, the x-axis, the blue x-axis is kind of becoming the y-axis, and the red y-axis on this is becoming the negative x-axis over here. So this is like post 90 degrees shift anti-clockwise, right? Anti-clockwise. So how do I create this effect? If this particular object or this particular diagram or input is given as a square, what kind of matrix multiplication or what kind of matrices I will use in combination so that the net effect, the output of that looks like it's flipping 90 degrees anti-clockwise. So that's kind of the whole equation, right? And in this case, it's more of a reflection. It's not flipping, but if you see here, the difference between this and this is the y-axis is still the same, but the x-axis, instead of going in the positive direction over here, it's coming in the negative direction. So it's like a mirror image, as if you're taking this y-axis as a mirror and then everything else you're taking as the reflection around the y-axis. How does it matter? So this and this are mirror reflections are on y-axis, and we'll come to that. The concept is same. Let's focus on the rotation here, okay? So if you do that, the magic is very simple. What is the matrix that we're going to define here? If you see here, there are three matrices when you put in a specific format. For example, any matrix, if you multiply with this matrix, it will give you the net effect of a 90-degree counterclockwise, that is anti-clockwise rotation effect. That means if I take this matrix on the leftmost and apply it on this input. So let's say if I have two objects and let's say the coordinates of this matrices are given inside here as an input. Okay, this is kind of the square box that I'm getting, and I want to create the effect in B. I want to convert this into B. So I'm going to take this matrix on the leftmost, right? 90 degrees, this thing, right? Exactly, I'm going to copy it on the leftmost. The leftmost matrix will have the effect on the rightmost. That's how it is. That's the reason I need to code on the left side, right? Because the sequence of matrix matters, right? Like I discussed, A into B is not equal to B is equal to A, right? So it's not equal. So the sequence matters. So if I multiply this matrix over here, right? The input, this is the input here, by this matrix, the net output it will create will be this matrix over here. So after this, if I multiply these two matrices, let's say this is a rotation matrix and this is the input matrix, and if I multiply this, right, the net effect will be this matrix. This is a 90-degree anti-clockwise flip. So that's all it is, right? That's all it is. So if you want to flip it 90 degrees, you do this way. What if you want to flip it 180 degrees? Then you use this matrix over here in the center. If you see here, it's a combination of 0 and 1s, but if you see the positions of the 0 and 1s are changing, and that signs negative and positive changing. Like I said, matrix notation is very positional inside the matrix, how the numbers are moving around, and also what is the sequence of the multiplication. So if I just take this matrix over here, and instead of this, I take this as the transformational matrix, then the output will be as if I'm rotating it 180 degrees. So what will happen? This is the 90-degree flip here, if you see here right now, and I need to rotate it 90 degrees more to get the flip. So what it will look like is, this will look something of this sort, where this will be a blue line, and this will be a red line, and this will be a square, right? That's how it is. Like, again, I'm going to turn it 90 degrees, push it 90 degrees. This will come down and this will come here. So if I apply this matrix directly on this input, the net effect will be 180 degrees. Similarly, if I want to turn it one more time from this position, I want to do 3 times flipping, then I need to apply a 270 degrees counterclockwise matrix. So I'll be applying this. So that's what it means, right? Whenever you want to rotate a matrix, or if you're going to do a computer graphics or a program or anything where you need to show the rotational effect of that, whether clockwise or anti-clockwise, okay, by certain degrees, you use this kind of matrix. And if you know that you want to rotate it by a whole 90 degrees or multiples of 90 degrees, you can straight away take this matrices and it will create the effect for you. That's what it means, right? That's the beauty of the matrix multiplication, what kind of effect it creates. In the first example, in the last video, we were talking about scalar. Now we're talking about rotational. Like scalar is like, there will be number here, there will be number here, and rest will be 0. This will have the effect of a scaling up or scaling down. If I use this kind of matrices, the numbers as is, it will give me kind of a rotational effect of that. Okay, and let's see what else we have. Okay, all right, just like a curiosity question. What happens if I apply all these matrices together? Let's say this is matrix A, this is matrix B, and this is matrix C. Let's say I apply all of them, and let's say there is an input matrix here after this, like say D. Okay, this is input matrix, which is our original square position box over here. This is diagram A, right? Let's say if I have an input function here, and if I'm using 3 matrices back to back, so like A, B, C, D, where D is my input, what will be the net effect of that, right? That's the curiosity question. What will be the effect of that if I use it in net? It's very simple, right? As I said, each matrix will have a transformational effect on the matrix on the right side. So the leftmost matrix will have the transformational effect on the matrix adjacent to that in the right side. And matrix, you have to go from right to left, right? Over here like this. So what will happen is, this C will kind of transform, and this is C. So this C has an effect of 270 degrees counterclockwise. So this will rotate D 270 degrees first, okay, wherever that lands. Okay, this square here will land 270 degrees. It will flip 3 times in anti-clockwise direction. Okay, that's the first part. And now then this effect is done. Okay, then whatever is the matrix, whatever is the end result, this B will take, B is this, B has the effect of 180 degree counterclockwise rotation. So whatever is the net resultant post that 270 degree split, that will again move 180 degrees counterclockwise because of B's effect of transformation, and that is done. And last but not the least, A has an effect of 90 degree clockwise rotation, counterclockwise rotation. So whatever is the net result landing after B's transformation, that will again move 90 degree counterclockwise, and that will be a net result, right? That's how you can imagine. So any number of matrices you multiply, assume that starting from right to left, each one has a transformational effect on the one next to that. C will have a transformational effect on D, B will have a transformational effect on the net transformation that C has on D, and A will have a net transformation effect on the transformational effect that B has on this as a whole. Sorry about that. So that's what it kind of matters, right? So that's what you should understand, how the multiplication works. What does it actually mean? You should just think about some transformational effects going on. And yeah, and here is the example of the reflection, right? Like I said, this example on the square, this C, this is not a rotation, this is a reflection. You cannot rotate and get this position. See, the y-axis is still the y-axis, but the x-axis has changed the direction. You cannot compute C from A just by rotating. You need to have a reflection effect, right? How do I do a reflection effect? Where you see in the movies, there's a reflection effect. So what do they do is they apply this kind of matrices to get the reflection effect. For example, let's say this is your original image over here, some random image, right? And I want this image to have a reflection across the y-axis, and so assume that this is my mirror here, right? Whatever I'm drawing across, I keep a mirror here, and if this object reflects on this mirror, and what will be the mirror image? That will be something of this sort, right? This will just exactly be a mirror of across this axis, right? So what kind of matrice, and if this is my input, the coordinates of this matrices, or all the points on this are input, or each point is an input. What is, if this is my input, what is the transformational matrix I need to put on the left, which will transform the matrix on the right to give a reflected image across y-axis? In that case, this is my transformation matrix, where you see it's coded in a specific format. So whenever I take this matrix, no matter what, if I take this exact matrix and apply it on some matrix on the right side, it will give me a effect which will be a reflected image across y-axis. So on with this x-axis, where this x-axis is your mirror, and you want to get, this is the input, and you want the output to be a reflection across x-axis, and this will be the net output. So what is the transformational matrix that will give me this effect? In that case, this is your answer. And similarly, what will be the reflection across the origin, where your origin is your mirror, right? For example, you're keeping a mirror like this, and this is going to give you a mirror image in this, right? So what is that? What kind of transformational matrix I can use on this image as input to give me this output? And in that case, this is the one. So that's what the rotational or the reflection matrix mean, right? So we have covered scaling, we have covered rotation. In the next video, we'll cover shear, and straight away we'll jump into some of the syllabus specific examination problems, which is what matters. So far, I think I am helping you clear the understanding of how you should think about it, and then we'll straight jump into solving the problems and try to see how to get the scoring going on. Okay. So in closing, what I'm trying to tell is matrix multiplication in essence is transformation of some sort, and it's magical. And coming up next is shear, another sort of transformation, and that will be the last session I'll be doing before I take some real world examples and solve it from exam standpoint of view, guys. Stay tuned, and hopefully I'll see you in the next video.